Hello everybody, welcome back to the online course on computer organization and architecture. Now we are in the module input output subsystem. So in our last class we have discussed about the issues related to the input output, why IO module is required, and we have seen there are three ways of transfer information. One is your programmed IO, second one is your interrupt driven IO, and third one is your DMA. In last class, we have briefly discussed about the programmed IO. Now, in this unit, we are going to discuss about the interrupt driven IO. So, what are the objective of this particular unit? So, for that I have stated three objectives. Objective 1, discuss the need of interrupt driven IO transfer. This will be done in comprehension level. Objective 2, specify the control signal needed for interrupt driven IO transfer and their use. So, it will be in the analysis level. And objective 3, explain the design issues of interrupt driven IO transfer. So, it will be in the level design. So, basically we are going to see how to design an interrupt driven IO. So, already I have mentioned that there are three ways of transfer information. One is your programmed IO. So, in case of programmed IO, already we have discussed that we have some problem with this particular portion, that processor is going to check continuously whether device is ready or not. If it is not ready, then it will be in this particular loop and there are wastage of time. So, I say that processor is in idle state, doing nothing. So, one way to look into that particular issue and how we can remove this particular unnecessary waiting, where CPU time is wasted. So, for that, from programmed IO, we are coming to interrupt driven IO. So, in interrupt driven IO, what we are basically doing? We are trying to remove, or we have removed this particular busy waiting or idle cycle. So, in that particular case, what will happen? Processor will request for IO transfer, and after requesting it, now processor can do some other work, if really processor can do it, because again there are some issues related to this particular point, but if processor can carry out some other work, then processor can carry out that particular work. Then IO module is going to make the data ready for transfer, and that means it will look for the status of the device, it will collect the relevant information, and once everything is set, everything is ready, then IO module is going to give an interrupt signal to the processor. It will say that now device is ready, now we can transfer the information, then IO transfer is going to happen. So, in that particular way, what happens? We are eliminating this particular waiting state, busy waiting state, where processor is busy, but doing nothing. So, we can eliminate that, and processor can now do something else, provided it is available. Processor can do that particular work. So, once this is there, then the remaining portion is same. We are going to transfer the information from IO devices to processor, or from processor to IO devices. And finally, we are going to come out. Now, we are going to see what are the issues related to designing of this particular interrupt driven IO. So, basically I have explained these things, overcome CPU waiting, no repeated CPU checking to device, the way we used to do in our programmed IO, and IO modules interrupt when ready. So, when everything is ready, then IO modules interrupt the processor and says that now we are ready to transfer the information. So, these are the basic steps that we are having, or the advantage that we are having when we are going for interrupt driven IO, eliminating of busy waiting. Now, processor is not continuously going to take the status of the device. IO module is going to give the indication through interrupt signals. So, what are the basic operations that we have in case of interrupt driven IO? So, just so that CPU issues read command. So, here I am saying that read commands, but read commands means processor is going to take information from devices. If processor is going to put information to the output devices, then what will happen? Then processor issues write command. IO module gets data from peripheral while CPU does some other work. Now, that we are removing the busy waiting of the processor. Now, IO module is going to look into the transfer of information, it will get the data from the peripheral devices, and in the meantime CPU can carry out some other work. IO module interrupts CPU. So, when everything is ready, device is ready, IO module has collected the information that need to be transferred to the processor, then everything is ready, then IO module interrupt the CPU. Then after getting the interrupt request, then CPU request for data. We will see what are the steps that we are having, because processor is going to now look for that particular I/O devices. Then when CPU requests the data, then I/O modules transfer the data, and like that we are going to transfer the information from input device to the processor, and similarly the write operation is same, we are going to transfer information from processor to the output devices. Now, from CPU viewpoint, what are the action that we are going to do? Issues read command, and processor is going to sum the work, check the interrupt at the end of each instruction cycle. Now, we are going to elaborate these things, because we need to look for the end of the instruction. Okay. Now, I think you know how we are going to execute an instruction. Program is nothing but a collection of instruction, and we are going to execute it instruction by instruction, and what we are having, what information we are having with us, we know the address of the next instruction from where we need to fetch the next instruction, and we are keeping this particular information in program counter. You just see, to execute one instruction, basically I said that it may have two stages only, fetch and execute, or maybe we may have several stages also, because in execution phase we may have different stages like fetching of data, then carry out the operation, write the result, and like that. So, in all those cases you just see, we are having the information of next instruction only. We do not have those intermediate information where we are currently, what stage we are doing, whether we are fetching a data or we are executing the instruction or carry out the operation or we are writing the result. So, these things are not available with us, we are having only the information of the next instruction. That is why processor is going to look for the interrupt at the end of this particular instruction cycle. So, once complete instruction is over, then only we can give the service for the interrupted devices, because in between we do not have any checkpoint or any monitoring. We know only starting of the instruction and end of the instruction. So, instruction cycle must be completed, then only we can look for interrupt. Now, when we are going to give service to the interrupt, then what does it means? We have to perform some operation. Again, those operation can be treated as a collection of instruction, which is basically nothing but again another separate computer program. So, we are going to execute that program, and that program is basically known as your interrupt service routine. For different devices, we are having different interrupt service routine. So, basically we are going to stop the execution of the current program after completion of the current instruction, and we are going to run the interrupt service routine. Okay. So, that is why we are going to have run the interrupt service routine. Now, I think you can correlate this situation with the function call. I think we have discussed that issues when we are going to discuss about the instruction set design and how we are going to implement it. So, when we are going to execute a sub function or a subroutine, then what will happen? We temporarily suspend the execution of the main program. When we are going to suspend the execution of the main program, we have to store the processor status, and where we are storing the processor status? Basically, we are storing it in the system stack. So, we keep all those information in the system stack. That is why we are saying that if interrupted, save context, and we are going to save context means basically we are going to save the contents of the register, because those register will be used again by the interrupt service routine if these are general purpose register. Secondly, we have to store the content of the program counter event, because after completion of the interrupt service routine, we have to come back to the current program that we are executing. So, we must know where to come back. So, that is why we are going to store the contents of the program counter event. Again, we are going to store the PSW, program status word. So, PSW is nothing but the contents of the flag bits, because if we are performing one operation, depending on the result of operation, we may have to take some decision. But if we won't store it, and while executing the interrupt service routine, that flags bit may be changed, it may be disturbed. So, we are not going to get the initial status. So, that is why we need to save this particular PSW also, program status word. So, this is basically a context switching. We are switching a context from main program to the interrupt service routine. We are storing the context of the main program or the currently executing program in the system stack. Then we are going to load the program counter with the starting address of the interrupt service routine, and we are going to give the service to the interrupt. That means, we are going to process the interrupt. So, when we are going to process the interrupt, depending on the interrupt service routine, depending on the nature of the devices, we are going to fetch data or we are going to store it. So, if it is an input of devices, we are going to fetch it and we are going to keep it in our memory. If it is an output device, then we are going to take the information from memory and going to put it in the output device. So, process interrupt means basically transferring the information. Once the transfer is over, then what will happen? Again, we will come back to the main program or the program from where we have given the interrupt or giving the service to the interrupted devices. So, again we have to restore the information. That means, again we are going to bring the information from system stack to the processor. That means, we are going to restore all the registers value, we are going to restore the program status word, and along with that we are going to bring the program counter values also. Then we will be knowing from where we need to start the execution. So, from CPU viewpoint, we are going to say that these are the tasks that we need to do when we are going to give a service for interrupt. So, this is basically I have already explained that this is fetch, then execute, and execute may have several stages, or secondly in some of the instruction it needs indirect cycle, because we need to fetch the instruction. So, while we are performing one operation, we are basically doing this cycle. So, when executing a program, if interrupt arrives, so we are getting an interrupt from the interrupted devices or for I/O module, then what will happen? After completion of the instruction, before fetching the next instruction, we will go for the interrupted devices, or we are going to execute the interrupt service routine. At that particular point, first of all, we have to retain the processor status. We are going to push all the information to the system stack. Then we are going to execute the interrupt service routine to give the service for that interrupt, and after completion of that particular interrupt service routine, that means one data transfer is over, then we are going to restore back the processor status. That means, we are going to pick up the information from system stack and going to put into the relevant registers. So, these are the things that we are going to do. Basically, one is your, so basically it is a context switching, basically save the context of the processor. After saving the context, then process the interrupt, then we have to run the interrupt service routine. Then after completion of these things, restore the processor status. That means, we are going to get back the processor status from system stack, and we are going to restore everything in the appropriate register. So, this is the indirect cycle with indirect as well as with interrupt. Now, that what are the state diagram? We may have a slightly elaborate diagram. So, in that particular case, what will happen when we are going to execute an program or execute an instruction? First, we have to get the instruction address calculation. First, we have to say where from we have to fetch the instruction. So, this is basically nothing but we are going to get the information from program counter. Then we are going to fetch the instruction. After fetching the instruction, we have to decode the instruction. After decoding the instruction, we will be knowing whether is there any indirect cycle or not. Basically, we have to fetch some more data or not. So, if any indirect cycle is there, then what will happen? We have to calculate the operand address, fetch the operands, and if we need to fetch more operand, then it will be in this particular loop. Okay. And after completion of this particular indirection, then we will go for the operation, data operation. We perform the data operation, and finally, when we get the result, then we can sometimes we need to perform the operand address calculation. That means, in which memory location we are going to store our result. So, after getting this particular address, we are going to store the result or store the operand, and if we need to store more data, then it will be in this particular loop, because if sometimes we may work with the vector data also. So, one operand store is over, then it is the completion of the instruction, then we are coming to this particular step. In this particular step, what will happen? We are going to check whether any interrupts are pending or not. If interrupts are pending, then what will happen? We will go over here, we will give the service to the interrupted devices, and if no interrupt is coming, then straight away will coming over here and we will go for next address calculation. But in between I am having one more arrow. So, in that particular case, this is basically if we are working with the vector data or maybe say in an array. You just see that if I am going to add two arrays, then what will happen? We are performing the same operation addition, only data are different. So, I am having an array A and array B. If I am performing say AI plus BI, then what will happen? This operation is same. I am going to perform this addition operation. So, after performing A1 plus B1, then what will happen? Instead of going to look next instruction, new instruction, what will happen? We know that we have to perform this instruction itself. So, we have to only get the data. So, we are straight away coming to operand address calculation. That means, after 1 we will go to A2 and B2, A3 and B3. So, this is basically single instruction multiple data. If we are going to perform the same operation on multiple data, then we may design the processor in such a way that instead of fetching the instruction straight away, you can go for fetching the data. You just see what happens after completion of one instruction, we are going to check for the interrupt. If there is no interrupt, then what will happen? We will go back to the current program execution. But if any interrupt is pending, then what will happen? We will go for this particular interrupt state. That means, we are going to give service to the interrupted devices. In that particular case, we are going to save the status of the processor. We give the service to the interrupted devices, then we are going to restore the status of the processor and we come back to the program itself. So, we know that once we restore the status, we know from where we have to fetch the next instruction and accordingly we are going to execute the program itself. So, this is the complete instruction cycle state diagram. So, these are the states that we have during instruction execution. So, this is the elaborate view. Some of the instruction may not have all the states, but some of the instruction may have all the states. It depends on the type of the instruction, and after decoding the instruction, we will be knowing what are the state that we have for execution of this particular instruction. This is the complete instruction cycle state diagram, and these are the states that we have when we are going to execute an instruction. Now, already I have mentioned that how we are going to give the service to the interrupt. This is very much similar to the function call and return. So, what basically we are doing? So, basically what are the steps we are having? Device controller or other system hardware issues an interrupt. So, we are getting an interrupt, processor is getting an interrupt. Now, say processor finishes the execution of the current instruction. Now, we must complete the current instruction, because we do not have any mechanism to keep the information that what stage we are executing currently. So, that information, that such type of information we cannot retaining it. That is why we are going to complete the current instruction. After completion of the current instruction, we know from which memory location we need to fetch the next instruction. So, at that particular point we can stop it. So, after completion of the current instruction, what will happen? Processor signals acknowledgement of interrupt. Now, processor give an acknowledgement signal to the interrupted devices or to the interrupted I/O module. It says that now processor is free to give the service to the interrupted devices. Now, processor stall at that time. So, at that particular time, processor pushes the PSW and PC onto the control stack. Already I have mentioned that we are having a control stack. What are the basic information that I need to store? One is your program counter, because it will give me the information from where I need to fetch the next instruction of the current executing program. So, basically we are going to give a service to the interrupted devices, we have to retain it. So, we are going to retain this particular information, we are going to push it to the system stack. Along with that, we are going to store the PSW also, program status word. Already I have mentioned that these are nothing but, or this is nothing but a collection of all flag bits, and basically the flag bits is set or reset depending on the ALU operation. So, we have to retain these things, because when we are going to come back to the main program, then what will happen? Depending on the status, we may have to take some other decision. So, we are going to store it. Then processor loads the new PC value based on the interrupt. Now, I am saying that for every interrupt, we are having an interrupt service routine. So, basically now you see, if this is my main memory and say currently we are executing this particular program. Depending on these things, that service routine, say that may be your, this may be one, this may be your another interrupt service routine. So, we must know the starting address of this particular service routine. So, we are going to load the value of the program counter with the starting address of this particular interrupt service routine. That means, we are setting which program we need to execute. Now, processor is going to execute this particular program. After completion of this particular program, we will come back to this particular point. Wherever say we are interrupt is coming at that particular point. So, we will come back to this particular point. So, we are setting it, then along with that, before going to execute these things, we may have to some more information. So, save the remainder of the processor state information. So, what are the processor state information? We are say in this particular program, when we are executing this particular program, we might have used some general purpose register like that R1 and R2. They are having some valid result. So, when I am going to execute this particular subroutine, then what will happen? Again we have to use those particular temporary storage, those registers. So, in that particular case what will happen? That values will be overwritten by this particular service routine. So, we have to store that information also. So, after storing this information, now process the interrupt. Now, we are going to execute this particular service routine, and once we complete it, completion of this particular service routine, then we have to come back to that particular point. So, this is your restore the processor state. That means, we are restoring and we are coming back to that particular point. So, restoring means getting the PSW, getting the your program counter and getting the values of all the registers, and we are now coming to the initial position, and from that we are going to execute it. So, this is the processor state. Basically, these are nothing but the contents of the general purpose register. We are going to restore it, because we have to restore it in this particular order only, because we are using a system stack. This is push and pop, and stack is your last in first out. Whatever we have entered last, we have to pop out first and going to put it in the appropriate register. Then we are going to pop out program counter and PSW, and we are going to store it. Now, you just see that here it is mentioned that this is something is written as hardware and it is software. So, that means some portion we are going to do in the hardware level. That means, when we are going to design the instruction, we are going to put everything into the processor itself. So, up to this point we are doing it in the hardware level. Again, this particular point, basically though it is written over here, we can say that this is basically we are going to do into the software level. What we are doing, save the remainder of the state information, basically that storing the general purpose register value. Now, why we have shifted to the software side? Say if you think that we are having a processor with say 16 general purpose register. Okay. In that particular case, what will happen? All those 16 may be used in the main program. Again, we may require all those 16 processor may be in the subroutine. So, we do not know, we cannot predict anything. So, if we are going to do everything in hardware, then what will happen? We have to store the values of those particular 16 general purpose register also into the stack. That means, we have to push all those values of the 16 register to the stack. And after completion of these things, when we are going to use this particular restore it, then we have to again bring all those things to the processor. So, it is basically a very heavy instruction, because we have to do lot of work. But many a time you may find that out of 16 general purpose register, hardly we may be using say 4 registers in this particular program. So, that means the values of those 4 registers are relevant, other 12 registers are irrelevant. So, what we basically do, if we are going to do it into the software level, then we can check that information also, how many registers are active in this particular program segment, and depending on that only we are going to store those particular register only. So, it will be reduced also. So, that is why this portion when we are going to implement, this portion generally we are not implementing in your hardware. We generally keep it for the programmer. When programmer is going to write such type of service routine, depending on the situation in this particular interrupt service routine, programmer is going to store those particular register value into the stack, and after that it is going to perform the interrupt service routine. And after completion of the interrupt service routine, since that interrupt service routine knows that it has stored 4 registers value to the stack, it is going to pop out those particular 4 register values and store it into the processor register. So, after that the execution of this particular interrupt service routine is over, then again these things will be done in our hardware level. So, this is also will be done in your software. So, this will be done in our hardware level, that means again we are going to restore the processor status word and program counter. Okay. This is the word that we can say, or we can say that again maybe in program itself we can write it if we do not have any other instruction. So, these are the portion that we are doing in the hardware level. So, this is you just see that in interrupt we are implementing something in the hardware and we are implementing something into the software, just to have a balance. If we are going to do everything in hardware, then what will happen? This particular interrupt handling situation will be a complex one and it will be a heavy instruction. So, that is why something we are doing into the hardware and something we are doing into the software. So, you just see that I think similar scenario we are doing in the function call or subroutine call. So, in that particular case what will happen? This portion here instead of process of interrupt, this is basically your subroutine process. Execute the subroutine and this entire portion will be done into the software, that storing the values of general purpose register and restoring the general purpose register after completion of this particular subroutine, and this portion will be done with another instruction which is known as your return instruction in our instruction set. So, for subroutine call we are having one instruction for call, calling the subroutine, and one instruction is return to return from the subroutine. So, in that particular case this is the portion that we are going to do it in call. This portion will be done in the software and this portion will be done in the return instruction. So, the nature is same, execution of interrupt and execution of subroutine, but for your subroutine call we are calling it with the instruction call and returning it from with the instruction return, but in case of interrupt with an control signal we are initiating this process and after completion of these things we will go back to this particular point. So, this is the simple interrupt processing and these are the tasks we need to do while performing the interrupt. Now, what is the program status word? Already I have mentioned that these are nothing but a set of bits and this set of bits basically includes result of the last instruction that we have executed. One may be your sign bit, 0 bit, carry bit, equal bit and overflow bit. I think we have mentioned or we have discussed all those particular bits. Along with that we may have some other bits also. So, these are the bits basically affected by some ALU operation. So, programmer cannot set or reset those particular bits. Okay, these flag bits will be always affected by the result of an ALU, but along with that we are having some more flags also. One of the flag bits is your interrupt enable and disable. So, in that particular case when we are going to look for interrupt enable and disable. So, what basically we have said, this is the processor and this is a device, say CPU and say device. So, device is giving an interrupt. So, whenever its interrupt is coming, now processor, what processor will do? It will complete the execution of the current instruction and going to give service to the devices by indicating and with another signal called say acknowledgement signal. Now, what will happen if whenever you are doing, if some devices is going to interrupt, we are bound to give the service to the interrupted devices. But if processor is engaged in some important work, high priority work, just say in case of your this thing, say when we are looking for the aircraft control. So, in the control unit, then what will happen? We are monitoring the aircraft and accordingly we have to schedule the remaining aircraft. So, when it is doing that particular job, processor need not be interrupted by any other devices, because if it is going to give the service to that interrupted devices, that during that period something else may happen. So, in that particular case what will happen? We may have a provision to say whether we will allow interrupt or we will disallow interrupt. So, for that we are having a flag bit called interrupt enable. So, if you set it, then it says that we are enabling interrupt, that means during the execution of a particular program, any devices can interrupt the processor. If we set it to interrupt disable, then what will happen? We are disabling the interrupt, and in that particular case what will happen? If interrupt comes, then processor is not going to give the service to the interrupted devices. It will first complete the current program, after that only it will look for that particular interrupt devices. So, this is the way we can control it also, whether interrupt will be allowed or not. But there is a risk, there is a problem. Say you have written an interrupt service routine, okay, and your first instruction is say interrupt disable. We have disabled the interrupt and we have written your program. So, what will happen? After completion of the interrupt service routine, it will come to the main program. You have disabled the interrupt at that particular point. So, it remains disabled. So, after that processor is not going to give service to the interrupt, because it is already disabled. So, responsibility lies with the programmer who is going to write the interrupt service routine. If he writes interrupt disable, after completion of the interrupt service routine, he should enable it also, interrupt enable. So, this is basically I am talking about the interrupt service routine. So, while you are going to write your program also, when you are going to develop the software, if you feel that if you think that processor should not be interrupted while executing this particular program, so at the beginning you can disable it, but before completion, before coming out from this particular software, you should enable the interrupt. Otherwise, for remaining span, the interrupt will remain as disabled. So, processor is not going to give service to any of the devices. So, this responsibility lies with the programmer to enable it and disable it. So, that means this can be set and reset by a programmer, but other bits cannot be set and reset by a programmer, that will be set and reset by ALU person. Like that, similarly, we are having one particular flag bit, which is the supervisor mode. So, if you are working with a Unix system or Linux system, you may be knowing that we are having different kind of user. One is your root user, all of you know about it. So, if you are having a privilege of root user, you can do many more system operation, you can do many more things, you can set or reset many more things. But if you are in the user mode, then only you can work with the processor which is relevant to you only, you cannot touch any other system parameters. So, for that also what will happen, we can have a flag bits, and that flag bit will be set to either supervisor mode or non supervisor mode. So, for root generally we set it as a supervisor mode. So, when you log in as a root, then what will happen, you are having in the supervisor mode, now you can sense many more system parameter. But if you log in as an user, then you are not in supervisor or you are not having the supervisor mode. So, you can carry out only the work or the privilege assigned to you only, you cannot change any of the system parameters. So, such type of flag bits are also there, which can be set by the programmer. So, some bits are set by the programmer and some bits cannot be set by the programmer. So, combination of all those things are known as my program status word. So, this is a simple example, just say what will happen when we are going to perform the interrupt service routine. So, it says this is my user program. Okay. Currently, the values of program counter is n plus 1. So, what does it mean? That means we are executing this particular instruction that is available in this particular memory location n. Okay. Now, at that time while you are executing this thing, you just see that some interrupts has arrived. Then what processor will do? Processor will complete the execution of this instruction. After it is going to give the service to the interrupted devices. That means, it is going to execute the corresponding interrupt service routine. So, before going to start that interrupt service routine, what it needs to do? So, basically it shows like that. At that time, that value of the stack pointer is t. That means, this is my stack. So, stack pointer is pointing at that particular point. So, when it receives an interrupt, what it does? First, it is going to store those particular general purpose registers. So, we are pushing it to the control stack. After pushing these things to the control stack, then we are pushing this particular program counter value to the stack. Now, you just see that stack is now from t and we are putting some information now values of the stack pointer, that top of the stack is becoming the address t minus m. So, this t minus m is put into the stack pointer, because after completion of the service routine, we have to pop out from this particular point t minus m to t. So, once we put these things, then what will happen? Now, this is the interrupt service routine. It started from y and going to y plus l. So, the program counter values will be loaded with this particular address y. So, now we are set. Now, what will happen when we are going to fetch the next instruction? Then what will happen? We are going to fetch the instruction from this particular memory location y. So, like that, now we are going to execute the program that is available over here. Now, once it is done, once we complete this particular interrupt service routine, that return instruction is coming, then we have to restore the value. Now, what we are doing? You just see that first this is the top of the stack, we push pop it now, we are popping it to the y minus l, all the registers value that we have stored, we again we pop it out, and in accordingly it is going to push it over here. Now, accordingly that these values will be reduced, now top of the stack becomes t. Now, we are going to put this particular t to over here. So, when I am bringing this information, you just see now that program counter value is becoming n plus 1. Now, we are going to fetch the instruction that is in this memory location n plus 1. So, this is the way that we are giving service to the interrupted devices. We are storing the context, current context of the processor into the system stack, execute the interrupt service routine. After completion of the interrupt service routine, restore back the processor status and start executing the program from the next instruction. Now, this is the way that we are handling the interrupt. Okay, now, I think it is clear to us how we are handling the interrupt and how we are going to give service to the interrupted devices by running an interrupt service routine. Now, what are the design issues that we have? So, some of the issues that I have identified over here. How do we identify a module using the interrupt? Because already I am saying that there may be several I/O module. In every I/O module, we may connect several devices. So, we are going to work with a particular device, it will come through a particular I/O module. So, how to identify that particular module which is issuing the interrupt? How do we deal with the multiple interrupts? Now, say this is my main program. Okay. So, I am executing this particular instruction. At that point, one interrupt is coming. That means, I am running this particular interrupt service. So, from here we are coming to this particular interrupt service. When I am running this interrupt service routine, once some more interrupt is coming over here, say 1. So, another interrupt is coming over here. So, now what to do? Whether can I go for interrupt service routine 2, interrupt service routine 2, or whether I should execute this particular interrupt, then only I should go for this thing. So, these are the issues that we are having. So, how we are going to handle this particular interrupt? So, this is one issue, or secondly we may complete this particular interrupt, then we can go to this. So, basically it depends on the priorities that we are going to set with the interrupt. Okay. So, we will see these particular issues. So, these are the issues. Now, how to identify the module using the interrupt. This is the addressing scheme that already we have discussed when we discussed about the programmed I/O, and we have seen that how we are going to connect the I/O devices. We are having two ways to do it. One is your memory mapped I/O and second one is your isolated I/O. So, for all the modules we are having an address, but if several modules are connecting, so several addresses are there, how we will be knowing which module has given the interrupt. So, we have to identify the appropriate module. So, this is the issues how to identify it, but we know the addressing scheme. Through addressing scheme we can give address to each and every I/O module. So, there are different ways to do it to define identifying the interrupt module. One of issue is your different lines for each module. So, basically what will happen, say this is my processor. I am saying that I am having an line through which I can give interrupt. So, this may be your say I/O module 1. So, if interrupt is coming through this particular interrupt line 1, then I will be knowing that I have to give service to the interrupt module 1, I/O module 1. So, similarly, I can have another interrupt line where I am connecting say I/O module M2. Second module is connected to the interrupt line 2. So, if interrupt is coming through this particular interrupt line 2, then we know that it is coming from this I/O module 2. So, in that way we can resolve this issue, but how many lines you are going to provide? We do not know how many devices we are going to connect. Now, while we are designing the processor, we do not know where we are going to use it. Depending on the use of the processor, we are going to connect several devices. So, during design issues we cannot simply give the number of lines, we cannot freeze it, because any number may not be sufficient enough. Okay. So, for that what will happen, we have to look for a generic solution, so that that processor can be used for any situation, any number of devices can be used. So, for that one of the method is called software pool. Here we are going to use some software routine. CPU asks each module in turn. Okay. So, in that particular case what will happen? So, very simple way I can say that this is the software pool. Now, processor is going to run an routine, software routine to identify the I/O module which has given this particular interrupt. User SIP. After completion of the current instruction, we know that some interrupt request is there. Now, processor is going to give service to the interrupted devices. Now, if you are conducting several interrupted devices, now how to identify which module has given this particular interrupt. So, for that, before running the device service routine, it will run another software which may be a part of my operating system, which is known as your software pool. So, in that particular case, it says that CPU asks its module in time. Okay. Now, in that particular case, situation may be something like that. This is my processor. Okay. Through this particular interrupt line, we are connecting many more devices or many more I/O module. Say this is module 1, module 2, module 3. So, any module can give interrupt. Now, when processor is going to say that now it has got an interrupt, now it have to identify which module has given it. So, I am saying that in software pool it is going to run an software. So, in that particular case what will happen? Now, CPU branches to the interrupt service routine. In that particular case we are having the software poll each I/O module to determine which module caused the interrupt. So, first it will going to see check this particular module, okay, that service routine or say that software pool routine, whether interrupt is coming from this particular module or not. If it is not coming, then it will going to check for the next module. Okay. If it is not coming from it, then processor is going to check for the third module. So, this is the way it can look for it. So, it is going to pull each and every module, I/O module on each and every device to check which one has given the interrupt. Okay. So, this is the way it will identify, and once it will identify that this particular module is given the interrupt, accordingly it will place the addresses of this particular module and going to work with this particular module. So, now how to do these things. So, for doing these things we are having different approaches. One, it says that it can be done by separate command line test IO. So, we may have one command line or one control line. Through that particular control line it is going to give test IO. So, the processor raises the test IO and puts the addresses. So, what will happen? We can have a control signal called test IO and it will raise these things, and along with that it will give the address of this particular IO module. Then, if this particular module has generated the interrupt, then what will happen? Accordingly, it will respond to the processor that yes, it has done it. If it is not doing it, then it is not going to respond. Say not done it, then what will happen? This signal will go to the next module along with the appropriate address of this particular module, and this module will also behave like that. It has generated the interrupt, then it will respond to the processor. This is one way of doing it, which is known as your separate command line called test IO. The processor raises the test IO and places the address. The IO module responds positively if set the interrupt. So, this is one way. Second way is done it by addressable status register. So, basically what will happen? Already I said that for IO module, if I am having an IO module, then we are having called a status register. Okay. In last class I think I have explained it that we are having a status register. So, here we may have one bit position maybe which is known as your interrupt bit. Okay. So, when this IO module will set this particular interrupt, then what will happen? It will set this particular bit to 1. That means, it will indicate that interrupt has been raised by this particular module. So, in that particular case what will happen? This processor is going to check this particular status bit. So, when says that one interrupt, that processor has got an interrupt, then it will complete the execution of the current instruction, and now it is going to look for the giving service to the interrupted devices. Now, it is going to check this particular bit. If this is set, then it will be processor will be knowing that this module has given the interrupt, and accordingly processor will set the address of this module and going to carry out the work. If it is 0, then it is going to check the next module, and accordingly it will go this way. So, it is going from module to module just to check it whether who has raised the interrupt. So, this is another way to resolve it. So, these are the two ways we can resolve it. We can see which devices has or which IO module has raised the interrupt, and once we can identify it, then what will happen? We are going to run the appropriate service routine, interrupt service routine for that particular device. So, this is basically say we are doing into the software level. So, another one we are having an hardware level, and which is known as your hardware pool. It is similar to that particular pooling only, software pooling only, but it is done in the hardware level. So, we do not have any service routine. So, how we are doing it? You just see, say this is the processor. Now, say this is the interrupt line. Okay. So, to this particular interrupt line, module will be connected. So, this is the module 1, module 2, module 3, like that. Okay. Now, what will happen? When processor is going to give the getting an interrupt, then it should give the service to the processor. So, most of the processor is having one line called interrupt acknowledgement. So, basically this is the terminology we use, INT. INT basically look for says that this is the line interrupt line, and INTA is your interrupt acknowledgement. Okay. So, these are the two lines. So, now when processor is going to service to the interrupted devices, then it will set this particular interrupt acknowledgement to 1. It says that now processor is ready to give this. Now, when it will come to the first module, then what will happen? If that module has raise the interrupt, then it will capture this particular interrupt acknowledgement and accordingly it will place it in function, maybe address of this particular device to indicate that this module 1 has raised the interrupt. If module 1 has not raised the interrupt, then what will happen? It will pass this interrupt acknowledgement to the next devices. So, now next devices also act accordingly. If it has raised the interrupt, then it will give the indication to the processor along with its address. If it has not devised it, then it will pass the interrupt acknowledgement to M3. So, this is you just see that we are implementing these things in the hardware. So, that is why we are talking about it. This is the hardware pole, or the name given is your daisy chain, because devices are connected in a chain fashion, one after another in one chain itself. So, this is the things that we are doing, interrupt acknowledgement send down the chain. So, this is the chain. So, it will send down the chain. Module responsible places vector on bus. This vector basically nothing but the address of this particular devices to indicate that yes, it has done it. CPU uses vector to identify the handle routine. So, depending on those particular factor, what will happen? Now, processor is going to identify which service routine it needs to execute, and accordingly it will set the program counter value. So, this is one way, and another way is called bus master. So, we are having a bus master. So, basically what will happen? This is the processor, it is connected to say all the devices through this particular system bus. So, in case of bus master, what will happen? We are going to implement one more devices called bus master. So, in that particular case, what will happen? Whichever devices is going to give an interrupt, first of all it is going to echo the bus. That means, that bus will be used by that particular devices only. So, first of all devices or IO module is going to echo the bus, whichever is the IO module is echoing the bus, only that IO module or that device can raise the interrupt. So, it is now unique, only one device can raise the interrupt who has got the bus, because through bus master we are going to get the bus actually control of the bus. So, this system bus will be having a control to only one devices, and with the help of these things we are going to identify which module is going to give the interrupt. So, these are the ways that we are having. Now, how to handle multiple interrupts? So, in that particular case, one issue is like that we can have several interrupt lines, but this is limited. So, in that particular case, what will happen? Now, we have to handle these things. Now, already I said that when one interrupts come, we are giving a service to one interrupt service routine. At that time, another interrupt may come. So, now what decision we have to take? So, basically for each and every devices, we are going to give an priority, and generally it says that higher priority device cannot be interrupted by lower priority device. So, in the bus mastering only current master can interrupt. Okay. This is also another issue we have. So, we are assigning the priority. So, if processor is giving a service to a devices which is having higher priority, then that lower priority interrupt will remain pending. So, in that particular case, what will happen? This is the processor. So, this is a one interrupt service routine. So, interrupt may come over here. Okay. We will see if this interrupt is coming from a higher priority devices, then what will happen? Then we are going for the interrupt service routine of that higher priority devices. If the interrupt is coming from a lower priority device, then what will happen? Then we will complete this particular interrupt. After that only we are going to give the service to that particular interrupt service routine. So, this is the way we are going to handle it. Either immediately you can give it if the priority is higher, or otherwise we first complete the interrupt first, interrupt service routine first, then only we are going for the next interrupted devices. Now, how to issue these things? How to handle this particular interrupt? So, if we are having multiple line, then what will happen? Each line can have a priority. So, this is a higher priority line 1, this is the lower priority line, and this is the least priority line. So, those devices connected to the higher priority line will be always given the preference. On the other hand, say if I am having only one line and all the devices are connected to it, then what will happen? In that particular case, that we have to give service to the higher priority device. Now, you consider about the software poll, then what will happen? We are going to write the routine software poll routine in such a way that first it is going to check the status of the higher priority devices. If it is not interrupting, then we will go for the lower priority devices. Similarly, in case of your daisy chain, then higher priority devices will be electrically nearer to the processor. So, in this particular diagram, you just see that first M1 is going to get the interrupt acknowledgement. If it is not doing it, then it will give the pass the interrupt acknowledgement to the next module. So, higher priority module will be connected first, which will be electrically nearer to this particular processor. So, in this particular connection, M1 is having the highest priority, then M2, then M3. So, this is the way we can resolve it. So, that means, while connecting the devices, we have to resolve the priority issues. So, this is the issues that we have while designing an interrupt, and while designing the interrupt processor, then we have to integrate all those things while designing the processor itself. So, there is one simple example I am giving. So, we are talking about the 80x86 family. So, when we are having that say 80486, 80386 processor. So, for that processor we are having an interrupt and controller. So, 8259A is a interrupt controller. So, to that interrupt controller we can connect 8 lines. It is having 8 interrupt lines, that means we can connect 8 devices to it. Okay. Again, this particular 8259A can be connected in cascade fashion also. So, if we are having more devices, then we can use these things in cascade to incorporate more devices. So, one simple example. So, what is the sequence of event? You just see, I will show the example also. 8259A accept interrupts. Okay. So, devices are connected to 8259A, it accept the interrupts from the devices. 8259 say determines the priority. So, again that priority determination priority is not posed to the processor itself. So, 8259A is going to determine the priority, which is having the highest priority, which is having the lowest priority, like that. Once it is getting this particular resolving that particular issue, then 8259A signals 8086 through an interrupt line. So, 8086 is having an INTR line, interrupt line. So, once it identify the devices, once it find out the priority that it can be now service can be given to it, then 8259A give the interrupt signals to 8086, then CPU acknowledges, then 8086 acknowledges for it. When it will acknowledge? After completion of the current instruction. Then 8259A puts the correct vector on the data bus. Now, say to 8259A we are connecting 8 different devices, or even we can connect more. So, it will put the correct vector, appropriate vector, that means every device is having some unique ID or say unique address. So, it will put these things. After getting that information, now CPU process the interrupt. Now, what will happen? Once it gets the correct vector, then processor will be knowing which interrupt service routine we have to processor need to execute. It is going to execute that particular interrupt service routine. So, this is the way I am saying that we can connect more devices. Now, say this is the processor. Now, currently we are talking about 80268. It is that 82598. So, this is working as a master, it is going to give this interrupt signal. Now, say here I can connect 8 different devices from in IR0 to IR7, but instead of connecting the devices to those particular line, we are connecting another controller. Now, here we are connecting all the devices. So, in that particular case, you just see that we can connect 64 devices in this particular arrangement. So, 8 devices in the first, when interrupt is coming from this particular interrupt controller, basically this interrupt is related to device 0 to device 7. Again, if it is coming from this particular interrupt, then what will happen? Again, it is related to some other 8 devices. So, like that we are having 64 devices. Now, this controller is going to resolve from where it is going to get it. So, if it is going to get it from in the IR0, that means it is related to those particular device 0 to 7. Accordingly, it will give the interrupt. When it gets the interrupt acknowledgement, then it will put the, this controller will put the appropriate vectors. It will give the appropriate vector to the processor, that means appropriate address of this particular device who has interrupted it. So, this is the way we are going to connect IO devices to the processor. So, it can be cascaded also. So, these are specifics. Now, we are talking about 80x86. So, to connect the devices in the interrupt mode, we have to take help of this particular interrupt controller. For other families, for other processor, we have to use the corresponding interrupt controller. So, for every processor, we are having an interrupt controller. So, this is the way we are connecting and we are doing data transfer with the help of your interrupt driven IO. So, with this, now I am coming to the end. Now, you just see the some test item. So, first test item talking about saying that what is the major issues with program IO technique for data transfer, how can it be handled. So, this is the objective one, because we know the problem, what is the problem in program IO. To handle it, we are coming to interrupt driven IO. Question 2, explain using examples how data transfer is performed between CPU and IO devices using interrupt based IO technique. How does it resolve the issues with program based IO? So, this is basically objective 1 and 2. So, basically already we have explained how we are performing the IO transfer in interrupt driven these things, and I think you know what is the difference now with respect to program IO. Test item 3, question 3, what are the different types of interrupts? Explain with example where each type is applicable. So, basically you just say that what are the different type of interrupts that we may have. So, something with coming from IO devices itself, something are coming from IO modules, and all those interrupts may have different priorities. So, how we are going to handle. Okay. Question 4, if there are multiple devices working on interrupt based IO, how does CPU decide on their priorities? So, basically here in 8086 family, I say that priority has been given to your interrupt handler, interrupt controller, but on the other hand, if it is a daisy chain method, then what will happen? That while connecting the devices, we have to resolve it. If we are using your software poll, then while writing the software poll routine, we have to resolve it. So, these are the issues that we are having, how to handle the priorities, and you have to appropriately do it. So, with this, I will wind up this particular lecture. Thank you all.